for now. So, okay, so and Sean can join whenever he wants to. It's a really small class today, anyways. Okay, so today is the first day of the Combinatorics lecture for ALP. This is week 1, and basically how it works is that each week we are going to cover a different topic in Combinatorics, and the classes are meant to sort of build upon each other, but so we encourage you to attend all of them, right? Like all of them in succession, so you can like take them as a class, but you do what you can do what you want. It's not as much as a class as like the summations mini course, which was actually structured like a course if we actually took the summations mini course. But anyways, going off on a tangent. But okay, so today we're covering basic counting techniques. But before we get into that, I guess I'll give a brief introduction. So my name is Evan. I'm a rising sophomore at High Technology High School. Things you should know about me. My favorite color is purple. Combo used to be my least favorite subject. Now algebra is my least favorite subject, and also it's spelled with an O at the end. It's not spelled with an I at the end. If you spell it with an I at the end, then you might as well get out of here now. So, and my TAs are Caitlin, who is very good at Combinatorics, and Yishan, who I don't know who he is now, but he should be joining soon. Okay, so what will we do today? So today we will covering some the very basics, right? The very most elementary techniques. I'm starting from the ground up essentially. So what I'm going to cover today is going to be very boring. It's going to be very to a lot of you, it's going to be very boring. It's going to be a lot of review, but at the same time, I do want to build like a very good foundation, because what I see a lot of time is like people always going to all these advanced techniques, right? All these advanced techniques in combinatorics, and they always struggle. And I think the reason why they struggle is because they don't have their fundamentals, right? They don't know how have like the basic solid knowledge about like the basics of how combinatorics works, right? What it is, the basic strategies for doing it, right? So combinatorics is something that I think you should tackle it with a very clear strategy in mind, right? Like almost like a philosophy of sorts, right? So you should always come with a clear plan. You should look at the problem, and then you should come up with a clear plan on what you're going to do with the problem. It's not like so like in geometry problems, right? You always do draw a diagram, right? So in combinatorics problems, you should really, instead of drawing a diagram, you might want to like outline your steps, outline your thoughts, outline what your plan of action is on the problem. So that's I think if you outline your plan of action on a combinatorics problem, it usually makes it a little bit easier to comprehend, right? It makes it a little bit easier to deal with piece by piece, instead of it's like all a big mess of whatever this, whatever that jumbo. So what I want you to do is just so I want to cover the elementary ideas, the elementary strategies that you'll be using throughout your journey in competitive math, basically. Okay, so that's enough. So what is combinatorics? Well, to do that, so combinatorics, I usually think of it as the study of counting things, although there are other elements of combinatorics like probability, expected value, which aren't always counting related. They can, but at its most fundamental, combinatorics is like the study of counting things, right? So counting is all about asking like how many. You're asking to like find the number of a certain number of things. So and that's like very and so a lot of times in like competitive math, like most competitive math at least, it's always asking you to find the number of certain number of things. So combinatoric ideas like casework, constructive counting, they're also found in other subjects, right? Like number theory, algebra, even geometry sometimes, I don't know. But they still always use these, a lot of times they still always use these fundamental ideas, right? About how to find a certain number of things. So those are ideas that are not just like for combinatorics, they're also used for other subjects. So what about basic examples, right? So you might, so like elementary competition, they might ask you to find like how many circles are in this array, and you would just go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 circles. But there's so that's one way to count things, right? You just count things like in a very boring, very basic way. You counting them like 1, 2, 3, 4, one by one, like, and then eventually, if you list them, usually if you list everything out, you count everything out, you will get your final answer. And actually, a decent amount of counting problems can actually be done in this way. Like this is actually, so just one by one counting. It's the most basic idea, where you list everything out and then count them one by one. And you might be asking me, why am I talking about this? Why are we covering such a boring and basic idea? And the actual thing is that a lot of the earlier AMC level problems, this is basically all you need to solve them, right? So you just have to list everything that satisfies it, and then you just count them up one by one. It's very, so you do like this one by one counting, and I've actually seen like a lot of people, they sort of like bash these really hard, decently hard questions, right? Like decently hard AME questions, decently hard AMC questions. All they do is that they're just like so quick and so fast that they just list everything out and just count them one by one. And then if they're careful, they'll just get the same answer. They'll get the correct answer. Yeah, like AOIME number 9, that question, like I've heard of people who just like listed everything out because they were just so dumbfounded about the statement. And sometimes it will work. Sometimes listing everything out will actually turn out to be the best option. And that's a lot thing that a lot of people forget about. They're always trying to find like the neatest way, or like the way that requires like the least multiplication, addition, whatever. Sometimes you just have to do things in a very stupid way, and that's in a computational setting, that's perfectly fine. You can do things in a very stupid way. But okay, that's enough on that, because there are other better ways of counting, right? So you can think of it as like 5, 4, 3, 2, 1. That's 15. You add them up. Or you can maybe think of it as like this array as like half of a rectangle. If you really want to be a real smart person, you can go like 6 times 5 over 2 equals 15, right? There's many different ways of counting basic number of things, which is a very core idea. So okay, so on to example, right? So okay, so this is like a basic counting example. They use this in a lot of like math counts. You see this in math counts, AMC, it's everywhere. So like how many how many even integers are between -69 and 2021 inclusive, right? So they're asking you for like the number of integers between two numbers. And then what you do for these types of problems, it's a very simple idea. Well, at least what I like to, everyone has their own idea, but what I like to do for these boring problems is I find the smallest even integer and I find the largest even integer. And then I think about how many, and I calculate the difference between those two integers. So that's 2088. So the difference between these two numbers is 2088. So if you list out all of the even integers, there's going to be 144 gaps, right? There's going to be 144 gaps between 1044 gaps between consecutive even integers. So one thing you cannot forget is that the answer to this question is not just 1044. If you do this, it's called an off by 1, because your answer to this question is off by 1, and then you'll get 0 points and it'll be very sad. So for these questions, you actually have to add 1, because there's 1044 gaps, but they're actually separating 1045 even integers, right? So if there's one gap, there's 2, 3 gaps, there's 3, and so on. I'm sure you know what I'm talking about by now, but when you're, so this is another fundamental example, right? So you don't want to, when you're counting things, one of the most common mistakes is to miss something on the edge, right? You're going to miss something on like the edge, like you're going to miss the, what do you mean? There's 1045 numbers. Did I do stupid? So one of the, I calculated the difference between the two numbers. So I thought of it, I think of these problems as like 1044 gaps, which is 2088 divided by 2, and then they're separating this number of the number of gaps plus 1 to get your answer. That's how I think about it. I don't know. You can have your own way of thinking about it. But the general idea is that there's always this idea that of missing something on the edge, right? An edge case. This is something that goes through all of math. A lot of times you're going to miss something on the edge, like maybe like the least, the greatest, the weirdest, the least weirdest, whatever. You're going to miss some of these cases, and then you're just going to end up with an answer that's close to the real answer, but it's like 1 off, 2 off, something like that. And then you'll get no points and it'll be very sad. So you should never forget about the cases on the edge, right? In counting, you should never forget about the cases that you might not be thinking about the most often, but they're still there and you need to count them. Okay, so bijections is another key idea in combinatorics. So that's counting one thing in 2 different ways, right? So traditional example of this is like how many circles are in this array. You can think of it as like 5 plus 5 plus 5 plus 5, 1 for each of these rows. That gives us 20. Or you can think of it, count by columns. You can count by the columns. You can go from 4 plus 4 plus 4 plus 4 plus 4. And this is a very elementary example of a bijection, which is basically counting one thing in 2 different ways. That's the if you go into higher level math, you'll see that it's not exactly like this, but this is the most elementary way of explaining what a bijection is. It's counting one thing in two different ways. So you could choose to count it in one type of way, or you can choose it to count it in another type of way. And both of ways are going to end up with the same correct answer. So a lot of times in combinatoric problems, you're trying to find the best way to count something, right? You're trying to avoid the stupid way of counting something, like counting one by one by one by one. You want to try to find a way to count something that requires the least computation and the least work on your end. So that's bijections for you. So, and this will become more important in later classes. So it just seems like mindless words right now. Okay, so now let's go. Okay, I did these out of order. So let's go to the three main ways of counting, right? I think of these as the three main ways of counting. Other people have different ways of teaching it. I don't really care. So the first way of counting is what we call constructive counting, right? So so constructive counting, I always think of it as sort of multiplying, I guess. So so you have like you have like a given number of different things, and then what you do in constructive counting is that you choose one of the things first, then you count how many ways you can choose another of the things. You might choose how many ways to choose for another things. You have a bunch of random variables. Each variables corresponds to one thing, and then you multiply all of these together, and then you get your final result, right? So constructive counting is all about multiplying, right? So like, I don't know, how many two-letter words in the so like how many two-letter words in the alphabet. So what I mean by that is, first you can choose the first letter of the word. There's 26 choices there. Then you multiply it by 26 again to decide the second letter of the word. So that's an elementary example of constructive counting. So a more difficult example, I guess, is how many three-digit integers have only all even digits, right? There's no odd digits anywhere in that three-digit integer. So if you want to count the number of three-digit integers with this property, you can actually go digit by digit. You can go the first digit, which is like, it can be 2, 2, 4, 6, 8, not 0. Remember the thing about leading zeros. So there's 4 choices for the first digit. Second digit can be 0, 2, 4, 6, 8. So that's 5 choices there. And the third digit you can choose in 5 ways as well, because it's 0, 2, 4, 6, 8 again. So you end up with 100 three-digit integers with all even digits. And as you can see, it's much easier than just listing all the three-digit integers out and just counting all the ones with all even digits, like a very stupid person would do. So this is constructive counting, and constructive counting, you can think of it as being all about multiplication, right? You're multiplying one element, then multiplying another element, then multiplying another element of the thing you're counting about. Yeah, you can think of it. Yeah, so bijection is 2 ways of counting the same thing. That's how I think about it. Although there's other definitions, things get a little bit messy. Okay, I did things out of order. So now on to everyone's least favorite, counting technique, which is casework. So casework is all about adding. So you basically what you do is you split the things you want to count, you split it into several other things. You split the things that you want to count into several other subsets, I guess, that turn out to be a little bit easier to count, right? So an example of this is how many 3-digit integers have exactly one instance of the digit 1, all right? So in this case, you're going to use casework and constructive counting. That's why I said I did this out of order, because I'm stupid. But anyways, for this one, right, the way you split the things you want to count is very easy. You split it based on whether the 3-digit integer has the digit 1 in its 100th place, its 10th place, or its units place, right? So if it has a digit 1 in its 100th place, then there's 10 choices for the second digit and 10 choices for the third digit. If the digit 1 is in the 10th digit, then there's 9 ways to decide the 100th digit and 10 ways to decide the units digit, right? If the digit 1 is in the units place, and there's 9 ways to decide the 100th place, and there's 10 ways to decide the tens place, right? So what we've done is split our counting into 3 different constructive counting problems, right? So now we just compute each of these constructive counting problems, 100, 90, 90. And the trick is that you can add these up. You can add these up to get the total answer, right? So that's the beauty of casework counting. Casework counting is all about splitting something that's a little bit weird to deal with and splitting it into parts that are more easily manageable. So the 2 things that you must be careful about is, one, that there's no overlap between the cases, right? So the cases cannot, so one element of the things you want to count, it can't appear in like multiple cases. Otherwise, you're going to be over counting, right? You're going to be counting more because you've counted one thing twice, 3 times. Who knows how much you've over counted it. So you can't have overlap in your cases. So the only reason why wait, come on. Okay, I made a mistake. So, okay. Did anyone tell? Yeah, exactly 1 instance of my digit 1. So, okay. Okay. All right. Okay. 998989 80 81 72 72, and the answer is 225. Let's just forget that happened. Let's just forget that even happened. Did not happen. So yeah, so it's actually exactly 1 instance of the digit 1, right? This is the key word in the problem, and I forgot about it when I was doing it for you. But yeah, exactly 1, right? If it just said, if it said something like at least one instance of the digit 1, then we would actually be overcounting things because something that with a digit in the 100th place and the 10th place, it might be counted once here and it might be counted once here, depending on how we count our cases, right? So we don't want our cases to overlap. We don't want something to appear in multiple cases because that would be bad. And the other thing you need to be careful about is make sure that there's nothing missing. There's nothing missing. So this is another common example I see, right? People are gonna sum up several cases and they miss something on the edge, right? They miss some case that they haven't previously considered because they weren't being careful. So if so you have to make sure that there's nothing missing. So if you make sure that there's nothing missing and there's no overlap, then you ensure that everything is counted exactly once, and then you'll always get the answer that you want. At 20, at least one. I really have no clue. I haven't worked out the computation. Okay, here. It's almost the same problem. We'll do it now. Okay, so complementary counting is probably my favorite of the three. So in complementary counting, you're subtracting the stuff you don't want, right? So you're starting with something and then you're subtracting everything you don't want. And it's sort of like, so you're starting with like the total amount of things, you subtract the things that you don't want, which turns out to be easier to count than the things that you do want. And then after that, you end up with the things that you do want. So your total number of things minus things you don't want, then you get the things you do want. That is the idea. So example of this is how many 3-digit integers with at least one appearance of the digit 3, right? So in this case, you're starting with how many, so what are you going to be, what's the total that you're dealing with? So you want to choose the total number of things very carefully so that the things that you don't want that are still in that total is easier to count, right? So you start with the total number of things and you choose this total very carefully such that the things that you don't want that are still in this total are still easy to count, essentially. So how many 3-digit integers with at least one appearance of the digit 3? So in this case, the total is pretty obvious. It's the total number of 3-digit integers, which is just 900. I'll leave that to you to verify. It's just 9 times 10 times 10. Then you minus, since at least one, you're minusing the 3-digit integers with no appearance of the digit 3. So that turns out to be 8 times 9 times 9. I'll leave that to you to verify. So 900 minus 648, that comes out to 252. So yes, you're correct with that. So that is complementary counting. You're starting with a total that you choose in a clever way, and then you subtract the things that you don't want that are in that total, and you end up with the things that you do want. So you're often using these together, right? You're often using these things together. So you might have a casework problem. So one of these cases could just be like a 1 by 1, like a very stupid way of counting it. So one of the cases could be counted in a very stupid way because there's not enough elements in that case. One of the cases could be constructive, one of these cases could be complementary, and then you just have to figure these out, right? You're just applying these in counting problems. You're just applying these three strategies over and over and over again, so that, and the ultimate goal is everything is counted once. You want everything to be counted once. So that's the ultimate goal of all of this nonsense, right? So a lot of times you'll see counting problems with just a ton of cases, a ton of computation. But yeah, so these three counting techniques, they're very elementary, so they're often used in conjunction with each other, right? Yeah, so well, we're nowhere near conditional probability, but Nike likes to go psycho with the POTD. It's not my fault. So anyways, so on to our first actual problem, which is from the 2017 AMC 10A, number 8. At a gathering of 30 people, 20 people, there are 20 people who all know each other. So I guess you can think of it as 20 people who all know each other in this group. And then, oops, I left this out because I was lazy, but the 10 people who are left do not. So 20 people who know everyone, okay. 20 people who know everyone. Wait, I'm sorry. Everyone. Wait. Am I reading this question correctly? So next way. There are 10 people. Okay, so there are 10 people so 20 people who know everyone in their subgroup, right? And 10 people who know no one. So these 10 people know no one out of the 30 people. And these 20 people, this group of 20 people, every 2 people, they know each other, right? So people who know each other hug, and other people who don't know each other shake hands. And how many handshakes occur, right? So how many handshakes occur? So handshakes occur. So we're trying to find pairs of people who don't know each other, right? Because people who don't know each other shake hands. We're trying to find pairs of people who don't know each other. We're trying to find this. So okay. So what we do in this case is that we start with We start with casework, I meant. So there's 2 cases. So the case 1 is that the people who don't know each other are from this group of people from the group of, so the people from the group of social outcasts, right? So pairs of people who don't know each other. So these are pairs of people who are from the same group of social outcasts. And pairs of people who don't know each other can also be someone from the 20 people group and a social outcast, right? So this case turns out to be pretty easy to deal with, because use constructive counting here. There's 20 ways to choose the person from the 20 person group, and there's 10 ways to choose the social outcast. So that's 300 people in this case. So people from the group of social outcasts, how many ways can you choose a pair, right? So you first you choose the first person, then you choose the second person, right? So so you might think that this is how you do it, and then so there's 90 ways to choose people from the group of social outcasts, like a pair of people from a group of social outcasts, and 20 times 10 from the 20-person group, and 10 for social outcasts, so you get 290. Or did we, right? Because is 290 really the answer here? Did anyone? Oops, I guess no one. Yes, so okay, so people caught my mistake, which is good because I was looking for that. So people from the group of social outcasts, each pair is actually counted twice. So you counted A, B in this group of social outcasts, but you also counted BA. And since the pairs are actually unordered, this is not good because we counted each pair 2 times. So in this case, we actually have to divide by 2 in order to get rid of the overcount, right? We're getting rid of the overcount now. So 45, so our answer is actually 45 plus 200 equals 245, which is the correct answer, and 290 is wrong. If you got 290 on the test, then you would have a sad time because 290 is actually an answer choice. It was an actual answer choice to the question. So it would have had a sad time. Okay. Another example from the 2018 AMC 8. How many perfect cubes are between 2 to the power of 8 plus 1 and 2 to the power of 18 plus 1 inclusive, right? So you're counting number of perfect cubes between 2 to the power of 8 plus 1. That turns out to be 256. And 2 to the power of 18 plus 1, I'm not going to write out right now because it's not in the mood. 257, not 256. So the smallest cube greater than this number is 343. And the greatest cube less than this number actually turns out to just be 2 to the power of 18 over 6, which is, no, 2 to the power of 18 over 3, which is 2 to the power of 6. Got ahead of myself. So this cubed is the greatest cube less than 2 to the power of 18 plus 1. So that turns out to be 64. This turns out to be 13. Sorry. Right. No. 7 to the power of 3. There we go. So we're finally trying to find a number of perfect cubes between these two numbers. So you might just want to list them out. 7 cubed, 8 cubed, plus 7, 8 cubed, 8 cubed, 9 cubed, 10 cubed, 11 cubed, one by one, right? And you'll be there all day. But the truth is, there's a better way to count it, and the way you count it is just count the integers from 7 to 64 inclusive, right? Because each integer from 7 to 64, it's corresponding to a cube, right? It's corresponding to a cube between 7 cubed to 64 cubed inclusive, right? And I'll maybe if I illustrate it, it'll make more sense. But anyways, you can see here that we're just counting the number of integers between 64 and 7. So that our answer is 64 minus 7 plus 1 equals 58 in this case. So once again, you don't want to just subtract 64 and 7, right? If you got 60, if you just subtracted these two, you would get 57, but that would be one off, and you would actually be filling in Yeah, 57 was an answer on the question. So you would have had a very sad time. You would have had like a 24 or something instead of 25. What a tragedy. So we have 58 perfect cubes between these two numbers. All right, so on to the next idea, which is overcounting, which we've somewhat covered before, right? But so you already covered the type of overcounting where it's like you start with a total and you subtract the things you don't want. So you subtract the things you don't want. So that's complementary counting, right? Complementary counting. So, but another method of overcounting is like you count two cases with an overlap, then you subtract the overlap. So let's say you wanted to count the number of circles in this array right here. So this is a little bit stupid, but one way you can think about it is you count the number of dots in this rectangle, which is 2 times 5, then the number of circles in this red rectangle, which is 2 times 5 again, but you counted this little square of circles twice, so you subtract that once, 2 times 2, and you actually get your final answer of 2. You can get your final answer of 30. No, right. Get your final answer of 16. There we go. So that's just an elementary example of overcounting. Another way you can think about it is like this Venn diagram here, right? You count everything on this end, then everything on this end, then you subtract the region in between. So this actually becomes something known as the principle of inclusion or exclusion, or just pi. But that's a little bit advanced, so we won't get into that now. But this is essentially the gist of it, right? You're overcounting, then you subtract the things that you've overcounted, and you do this in order to make sure that you do this to make sure that everything you counted appears once and exactly once, essentially. Okay. Onto an example. So wait, this is not dealing with overcounting because I had my things messed up. Okay. So okay, why not go to actual overcounting question, right? So this is the famous 2020 Amy 1 problem 5. This is the problem that caused me a lot of pain when I first took the test back in 2020. I didn't actually do this question. I was just losing my mind because I couldn't figure out how to count what I wanted. I was caught lacking. I was caught lacking for this question. So okay, so the way this problem goes is that 6 cards, 1 through 6, are to be lined up in a row. Find the number of arrangements where a card can be removed that are leaving the remaining 5 cards in ascending, descending order, right? Yeah, so this is an example of one question where it is entirely possible for you to just list out everything and just cross out the ones you don't want, and then just counting one by one, doing something very stupid, and then you would end up with the final answer. So this is one of those questions where very stupid approach could work given enough time. But say you don't want to go through nearly as much pain, so you try to find a number of arrangements where a card can be removed, leaving the remaining 5 cards in ascending or descending order, right? So you first of all, you split it into 6 cases based on which card you remove that leaves the remaining 5 cards in ascending or descending order, right? So say you wanted, for each, like for 1, if you want to remove 1 and then the remaining 5 cards are in ascending or descending order, there's going to be 6 ways to choose the place of 1, after which everything is fixed. If it's going ascending, descending is the same thing. It's 6 again. So 6 plus 6. 2, once again, it's 6 plus 6. 3, again, it's 6 plus 6. And you just keep listing these out. 6 plus 6 equals 72. By now, you should understand that the number of arrangements for the ascending case is the same as the number of arrangements for the descending case. So you can just compute the ascending case and then multiply it by 2. But anyways, if you just put 72 here, you would be very wrong, because you actually turned out that you're actually overcounting several cases here. And cases you're overcounting is that where you can remove more than one possible card can be removed, and then leaving the rest in ascending, descending order. So for example, right, you're overcounting 1, 2, 3, 4, 5, 6. You actually counted this 6 times, once for each integer, right? So similarly, you also double counted 6, 5, 4, 3, 2, 1. You've also counted this 6 times. So you want to subtract 5, then you subtract 5 again, right? So you want to subtract 5 and get minus 5 again, you get 62. And if you put 62 in, you would also be wrong, because you're actually overcounting even more than that. You're actually overcounting cases like 1, 2, 1, 3, 4, 5, 6, or like 1, 3, 2, 4, 5, 6, right? So here you can remove any one of these 2, and you can remove any one of these 2, and then you would get the remaining 5 cards in ascending, descending order. So you actually have to subtract. So these cases, there's 5 of them, and you counted each of them twice. So you want to subtract 1 for each instance. So you actually subtract 5 for ascending, then you subtract 5 minus 5 for descending again. So I know I'm being a little bit hand wavy, but this is how you would have done it in the test, right? You would have noticed that these cases are overcounted once, and these cases are overcounted 5 times. So you just subtract 5 times minus 5, 1 for each case, minus 5, 1 for each case. So you get 72 minus 20 equals 52. And then if you were good at convincing yourself, then you would have thought that this was right, and you would have been right. So 52 is the final answer for this question. I know that a lot of people put like 60, 62, 72. They are all very common answers, right? This was a pretty tricky question, and I ultimately just I remember just guessing some random value because I was just so frustrated on dealing with this nasty problem. But goes to show if you approach things in a very systematic way, the problem actually isn't that daunting. Well, so the problem seems difficult when you first take it at face value, but if you take the time to analyze how to count it and how to strategically count everything exactly once, then it would have led you to this solution, right? Where you just count everything, then you subtract the things you don't want. So you can subtract this thing 5 times, subtract this thing 1 time for each appearance. And then eventually, once you've subtracted these things systematically, you would have ended up with your final answer. So the trick with these Amy combinatoric, like these casework things, you just have to keep your mind organized and keep your work organized. That's the most important thing. All right, back to this, which is more another casework example, I guess. Rabbits Peter and Pauline have 3 children, Flopsy, Mopsy, and Cottontail. They're very stupid names. These 5 rabbits are distributed to 4 different pet stores so that no store it gets both a parent and a child. So no store gets a parent and a parent and a child at the same time. And how many ways can this be done? So this is from the AMC 12A 2013, problem 15. So the key to this problem is to do casework. So the first case is that Peter and Pauline are, should I wait like 3 minutes so you can work on it? Sure, why not? I guess it's worth it. Do a little break. Okay, I can continue. Yeah. So the first case is that Peter and Pauline are together, right? They're together in the same store. That's that. So the first case is Peter and Pauline are in the same store, and the second case is Peter and Pauline are not in the same store. They're in different stores. So in the first case, there are 4 ways to choose the store that they're both in. And then each of the 3 children can go into each of the other 3 stores. So the first one can go into either of the 3, same with the second one, same with the third one. So that gives us 108 as our first case. Peter and Pauline are not together. So there's 4 ways to place Peter, I guess. 3 ways to place Pauline. And then each of the 3 children, now there's only 2 stores to choose from. 2 times 2 times 2 equals 96. So 108 plus 96 equals 204. So here, what we did, right, was we split it into cases. And once we split it into cases, the problem just became 2 very simple constructive counting problems. So a lot of times, this is a common theme with AMC 10 level problems. What you do is you split it into like a bunch of cases, and each case just ends up being like a really simple constructive counting problem. And then you just add all these little tiny cases up, and then you get your final answer. And the trick is to just make sure that you're adding correctly and you're multiplying correctly so you don't make a computation error. That's about it. These problems are pretty boring, but they show up decently frequently. So anyways, I guess I have a few more things to show. So these are, I'm going to show you like a few things that are these problems come up decently frequently, and they're about sets. They're about counting sets. They're about counting subsets of things, right? So let's say you have the integers from 1 to n. There's n elements, and you have to count how many subsets S of 1, 2, 3 all the way to n. How many total subsets? So then here, it's very simple. You just go element by element, So each of the elements, each element is in S or is not in S, right? So part of this is just approaching the problem in a very systematic way. You're constructing the subset S by looking at each element, the first element, second element, third element. It's very constructive, right? This is constructive counting. So there's 2 possibilities, and you do this for each of the elements, right? So 2 times 2 times 2 all the way. So there, just multiply 2 a bunch of times, once for each of the elements, and this ends up being 2 to the power of n, right? And the next thing you want to do, so another question that you might be asked, slightly less boring, is how many subsets S1, S2 of 1, 2, 3 all the way to n are there where S1 is a subset of S2, right? So how many pairs of subsets S1 and S2 of the integers from 1 to n are there where S1 is a subset of S2? So when you look at this question, there's like a bunch of subsets. S1 has to be a subset of S2. S2 is a subset of this even larger set, and it seems a little bit daunting, I guess. But the way you do this again is to look each element by element, right? You look each element by element. So each element in the big set can either be in S1 and S2. It can be in S2 only, but not S1, or it can be in S1, no, not in S1 or S2. This is the idea, right? So there's only 3 possibilities. The reason why we do this is that it allows us to deal with the condition that S1 is a subset of S2 very easily. Oh, why not 4? Yeah, so the case we're missing is in S1 but not in S2. But in that case, that would contradict the fact that S1 is a subset of S2, right? So this is our way of negating out the possibilities that we don't want. So there's only 3 possibilities. And once again, you do some repeated multiplication, 3 times 3 times 3, blah, blah. And you do this n times. This becomes 3 to the power of n, right? So okay, let's go a little bit further. Okay, so how many ordered? Okay, let me just add another page. How many ordered subsets? No, ordered 100 tuples, I guess, look like sequences of 100, order 1 tuple of sets S1, S2, S3, S100 of subsets of So how many ordered 100 tuples of subsets S1, S2, S3, all the way to S100 of the integers 1, 2, 3, 4, all the way up to n are there where S1 is a subset of S2, is a subset of S3, is a subset of S4, blah, 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 all the way to is a subset of S100, and we know that that is a subset of 1, 2, all the way up to n, right? So we're finding sequences of subsets where each subset is a subset of the next subset. And then you keep going along the sequence, and then they're all a subset of some bigger set, which is the integers from 1 to n, right? So this seems pretty, once again, this seems even more scary than the last one. But the what makes this so intriguing is that you can still apply the constructive idea. You look element by element, right? So for each element, it can be part of sets part of sets one. No, it can be part of sets like 1 to 100, 2 to 100, 3 to 100. It can be up to just 100, or it can be none at all, right? So it can be in all of the sets, right? It can be in this part of the sets. It can be in this part of the sets. This part of the sets, and you keep going with this, right? It can be part of the set only, or it can just be part of none of the sets. It's just this. It's just an integer. So once again, you're constructing your sequence of subsets by looking element by element of the integers from 1 to n. So I'll leave this. It's a little bit complicated to explain right now, but you're just essentially, each element can be part of a given part of the sequence, and then just not be a part of some other part of the sequence. And then if you keep doing this, I'll leave it to you to verify that there are actually 101 total possibilities for possibilities for each element of the integers from 1 all the way up to n. There's 101 possibilities. And once we have this, we've actually dealt with this weird subset condition is a subset of, is a subset of, is a subset of. We've actually dealt with it perfectly fine now by looking at it one element at a time. And yes, this argument easily generalizes to bigger and bigger numbers, right? I wouldn't be surprised if like the 100 gets replaced with like 2021. It gets used on some random competition soon, because this idea shows up decently often. I think it's decently cool. So I think this is a good example of just how powerful this constructive counting idea is, even though you might think it's very stupid at first, right? But anyways, there's 101 possibilities for each element, and that yields 101 to the power of n possibilities in total. That's our total right here. So, all right, so on to the last question, at least. So we might end a little bit early depending on how long it takes me to do this. But this was actually the last question in a recent competition. It was like the IMTC or something. I don't know. Like this guy called Puddles Penguin made it. But anyways, I just found this particular. It's the final question of the high school round. It's the hardest question on the test, apparently. He said that no one solved it, but I find it. So it's a hard question. There's no getting around that. But I find it so incredibly. Find it so incredibly neat. I really find it neat, and it really shows the power of this constructive counting approach, right? And I just really so Puddles Penguin. Puddles he makes good questions. This is one of the good questions. So the question goes like this. So this guy called Paul has a large number, an arbitrary amount of blocks with identical bases, identical sizes bases, and heights of 1, 2, 3, 4, and 5 units, right? With exactly 9 blocks, how many ways can Paul build 2 towers with the same height such that the bases not touching the ground have a unique elevation? So I guess one way to explain it would be something just to give you examples, right? So basically, you want the bases that are not touching the ground to have elevations above the ground that are distinct from each other, right? So having something like this, I guess, something like this. So anyway, so let me just keep constructing. So I have the two towers here. So each of the bases, so there's 9 blocks in total, 9 in total, 9 blocks in total. And each of the blocks has a unique elevation. So this base, there's no base that has the same elevation. This base, there's no other base that has the same elevation. Same with this one, this one, this one, this one, this one. right? Each of these 7 bases, they're on their own unique height. They're on their own unique elevation with respect to the ground. On the other hand, something like this, something like this, I don't know about the other top ones. This would not be okay, because look at these two. These two bases, they're on the same elevation. So these two towers, they would not be on these two towers, they will not be counted in our final count. This is bad. This is bad, because 2 of the bases, they end up having the same elevation, and that's not what we want. Okay? So anyways, so now let's see how exactly we approach this problem, right? So the problem with this problem, what makes it difficult is that it's just it's very hard to deal with this condition that the bases that are not touching the ground have the same elevation. No, the bases not touching the ground must have unique elevation, right? It's very hard to deal with this. So you can't really complementary count. It's a little bit tough to complementary count. You can try to use some advanced strategies, or you can do something stupid and just like do some random casework. But all these ways, they're not very good. And the truth is that the answer to this problem is actually pretty big. So it's not like there's much of a way that you can brute force this out using some using your knack for casework or something. So the way you do this is through constructive counting. So the critical idea is to think about building the towers from the ground up, 1 block at a time. So you might think, wait, you're going crazy here, because there's so many. If you build the towers 1 block at a time, how are you going to have bases not touching the ground? How are you going to have them have the unique elevation, right? How are we going to satisfy that constraint if we're building the towers from the ground up 1 block at a time? So yeah, so you would not, I don't think you would believe that this strategy actually works until you just have some kind of the audacity to just try it, to see how it works, just see how we might go about building the towers from the ground up 1 block at a time. And once you get this silly idea to just try it, and you would come up, with the following. Let me create a new page. So we start off by placing a block for the first tower. There's just 5 ways to choose the block for the first tower. Then there's 4 ways to choose the block for the second tower, because you can't have the tower of the same height as the first one, right? So there's 4 ways for the second tower. So you have 20 ways so far. So 20 ways gives you your first block of the first tower and your first block of the other tower. So now how do you go along? How do you go along? So the idea is the critical idea of this problem sort of magical in a way is that you can actually perform an algorithm that will always give you four ways to generate the next block. And the way you do this is look at the tower with lower height, and then next block you place on the tower of lower height, on lower height tower. And there's always going to be, it turns out there's always going to be four choices for this block. And the reason for this is that this lower tower is going to be it's going to be 1 to 4 units lower than the higher one. So if you place a block on lower tower, there's always going to be one block that you choose that's like a bad apple, right? So in this case, you can't choose 1, right? That would be bad. You can choose anything else. You can choose 2, you can choose 3, you can choose 4, you can choose 5. All of these work. And you can prove that there will always be 4 choices of the size of the next block that will always work. It's a bit of an inductive argument. But anyways, so you choose 4 blocks. No, there's 4 choices for the next block. So you choose, let's say, this block. Then you might choose this block, right? And then you choose this block. Notice that we're not necessarily alternating placing the blocks. So this tower actually gets another block because this tower is still lower. It's still lower. So you place another block. And then you go to this block, place another block, right? So you just place, so in this way, you can actually place, you can place 6 blocks in this way. You can place 6 blocks in this way. So there's 4 choices for each block, times 4 to the power of 6. So each place 6 blocks in this way, and now you just have one last block to place. One last block to place. Now you want the 2 towers to have the same height, right? And this turns out that there will always be exactly one way to choose the last block so that the 2 towers end up having the same height. So in this case, right, we would place the block with 2 on the lower tower, and any other choice would not work. Any other choice would force the towers to have different heights. So this is essentially how you finish the problem. So it's just, so now you've constructed the tower. So you've went about block by block using this algorithm of always placing on the lower tower. There's 4 choices for every block besides the first one, and then 1 for the last one. The last one is fixed. So to illustrate this, I guess I would go 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? This was how we placed our blocks here. And notice that even though one tower got many more blocks than the other, I guess that's one part of what makes this problem so challenging. We've successfully dealt with this by making us place the block on the lower tower, not necessarily like alternating towers, like what your intuition might lead you to believe, but we're actually just always placing on the lower tower, So in the end, we've come up with an algorithm that will always generate a pair of 2 towers, and it's pretty clear that every pair of 2 towers can also be reverse generated in this way, in a sense, if that makes any sense to you. So our answer actually just ends up being 5 times 4 times 4 to the power of 6 times 1, which is 5 times 4 to the power of 7. And that ends up becoming 81,920 is your final answer. So what I like about this problem, right, it shows the power of constructive counting. So the way you find a solution to this problem is really not supposed to work, right? Basically, at least to me, the fact that this solution actually works was very unintuitive, even to me, right? It's very intuitive that such a weird and sort of stupid strategy can actually magically work, right? And I find so in combinatorics often you just have to take a shot in the dark. You have to take a wild guess on how something can be computed, and if you're lucky enough, then you'll get it, and if you're not lucky enough, then at least you tried. So this is one of these problems. You just have to find a brilliant way of counting something, and then you magically get this neat answer. So once again, Puddles, Penguin, I'm giving him a shout out, writes good questions. Tell him I said hi. But yeah, so this was the last problem in the IMTC contest, which was held relatively recently. So I guess I've got to this conclusion a little bit early, but it's okay. So we can move along at a decently fast pace. So what did we do? So what we did was elementary counting techniques. So counting is all about asking how many, all about enumerating things, right? To do well at combinatorics, what you have to do is have a clear, systematic plan of action. You have to decide, what techniques does this problem seem to resemble? Where have I seen similar setups before, right? You should just be asking yourself these questions, all of these questions, to come up with a good strategy for this problem. So once you have a clear, systematic plan of action, that's when you can start to break the problem apart and make a scary problem seem not as scary anymore. So the three basic techniques are constructive, where you're constructing one component of the item that you're counting, one component at a time, and you're multiplying several numbers together to get your final answer. So multiply. You can do casework, where you're adding so you're splitting what you're counting into different sets that you can count on their own. So this is about adding, right? And the last thing is complementary counting, which is all about subtracting. It's all about subtracting things that you don't want from the total of things. And then by subtracting things you don't want, you end up with the things that you do want. And finally, we also talked a little bit about overcounting. And with overcounting, I like to think about the Venn diagram, right? You count one thing, you count the other thing, you subtract the things that they have in common. So, okay, so what to do for next week? If you have any questions, you can let me know. Through Discord, or just ping me in the community Discord or whatever. Look at the handout for this lecture, which should be coming out soon. It's written by Pigeon. Oh my god, why doesn't he name the field? Look at the handout by Pigeon. It's pretty instructive. He covers things in detail that I didn't cover in detail. And just keep practicing, I guess. Keep practicing. This, and then we'll see you. Yes, I'll see you back here for next week's class. Yeah, so